Hi, this video is to help explain how to write chemical formulas from the names. Now, the first step, ladies and gentlemen, is that you have to determine what type of compound you are dealing with. All right, if a compound starts with a metal but does not have Greek prefixes, then it's ionic. All right, for example, if it's sodium oxalate, this starts with a metal, all right, and there's no prefixes anywhere, so you know that it's going to be an ionic compound. If it is a compound that has Greek prefixes, like dinitrogen octoxide, then it has Greek prefixes, and therefore it's molecular. Plus, it starts with a non-metal. The third option, or the third type, is going to be an acid. For example, hydrochloric acid. You can tell this is an acid because it says the word acid. Now, once you've established what type of compound it is, there are three ways of going about writing the formulas. Now, the first one I'm going to talk to you about is how to write a chemical formula for a molecular compound, such as this one in the middle. These are very simple. You simply use the Greek prefix to tell you what the subscripts are for each element. In this case, we have nitrogen, so we write the symbol for nitrogen. It's dinitrogen. The Greek prefix for di, and the Greek prefix di means two. And then octoxide. Oct is the Greek prefix for 8. So we have oxide is oxygen. Remember the original element, you simply take off "ide" and figure out which element has ox in it. And the only one is oxygen. And then 8 for oxide. That's it. That's all you do for molecular compounds. Two elements, both nonmetals, and the Greek prefixes tell you what the subscripts are. Now, for acids, you're going to use the acid naming table, but backwards. For example, hydrochloric acid. Hydrochloric acid, the first step is you got to figure out what is the original root versus what is the add-on. If you look on the acid naming table, we see that we have three possibilities. You could be hydroic acid, OUS acid, or simply ic acid. In this case, if you notice, yes, it has ic acid, but it also has the prefix hydro, which means that it has to be this possibility. So we cross out all of the add-ons, and we simply have chlor. Now, the original anion ending, all right, for hydroic acid was "ide." All right, that's the one that matches that add-on. So we take the chlor and we write the IDE original ending. Now we figure out, well, what is the symbol and charge for this anion? Since it ends in "ide", chances are it's going to be monoatomic. There are, however, a couple of exceptions to that. If it ends in "ide", it could be, if you're looking on the back, it could be peroxide, it could be hydroxide, or it could be cyanide. Since it's neither of those three, we know it must be an individual element. So the question is, what element starts with chlor? And looking on the periodic table, we know it has to be a non-metal, so we stick to the right. And the answer, of course, is chlorine. So we look at the symbol, and we need to know the charge of that. Now, since chlorine is in column 17, we know that everything in column 17 has a -1 charge when it's an ion. We know that this is going to be a -1 charge. Now, when you're writing an acid's formula, remember, an acid is an ionic compound that has hydrogen ions as the cation. Simply, you put H in front of the anion, but you need one H per negative charge. So since there's only one negative charge, we erase the charge and write a single H in front. And then we end it off with an AQ. Let me show you another example of that. Let's say we have oxalic acid. Now, oxalic acid has ic acid as the ending. No hydro in front though. So looking on the acid naming table, it can't be this one. It doesn't have OUS acid at the end, but it does have ic acid, which means the original anion ending was 8. So we take oxyl, we get rid of the ic acid and add 8. Now, since it ends in 8, it has to be a polyatomic ion. 8 or ite ending means that it has to be a polyatomic anion, which means we look for oxalate on the back of our periodic table on this side that has the negative ions. And we look down for oxalate, and it's right here. Now the formula for it is C2O4, and the charge is -2. So C2O4, remember it has a -2 charge. We must put, since it's an acid, we have to put one hydrogen per negative charge in front of it. Since it's a -2, we put 2 hydrogens in front. We erase the charge, and since it's an acid, we must finish it off by including an AQ. So oxalic acid is H2CO4. One final example. Let's use one that has the pore Sur. For example, let's say we have H3PO3. Sorry, going the wrong direction. Let's say we have phosphorus acid. Now, here we have OUS acid, which means that the original anion ending was ite. But because we see phos, we look at the pore Sur rule, which says that when you're naming it, if it includes phosphorus, you add on an additional OR before the suffix. So we have to do that in reverse. Here is the additional OR. We have to get rid of that, as well as getting rid of the OUS acid. And we add on the original anion ending to the root phos. And the original anion ending for OUS acid was ite. So it is phosphite. We look on the back, since it ends in ite, it must be an anion that is on the back of the periodic table. So we look down for phosphite, it's right here. The formula is PO3, -3. PO3, -3. Since it's an acid, it must have one hydrogen in front for each negative charge. -3 means it's going to be H3PO3. We erase the negative charge, and we finish it off by having an AQ. Next, that is for the acids. The last one I want to talk to you about are writing formulas for ionic compounds. Now, the formulas for ionic compounds, ladies and gentlemen, are a little bit trickier because you have to figure it out based upon the charges. So let's take, for example, aluminum sulfide. Okay? Aluminum sulfide. It has a metal in front, aluminum. That's how we can tell it's an ionic compound. Now, the way to write out the formulas for these is You start off by writing the symbol and charge for both the cation and the anion. Aluminum, the symbol is Al, and since it is in column 13 on the periodic table, it therefore has a positive 3 charge. Next, we look at the anion, sulfide. It ends in "ide." Most likely, it is going to be a monoatomic anion. As I said before, there's only 3 polyatomic anions that end in "ide": peroxide, hydroxide, and cyanide. This has neither of them, or none of them, so this has to be a monoatomic anion. So what element begins with sulf? I'll look on our periodic table, and we see that it is sulfur. We also see that its symbol is S, and it is in column 16, so it has a -2 charge. Now, once we have the charges and symbols, we then do a simple trick to make sure that the compound is electroneutral, so that all the positives equal and cancel out with all the negatives. And we do that by doing a simple rule called cross, drop, and reduce. What that means is the number of the charge of the cation, not the charge, but the number of the charge, will cross over, drop down, and become the subscript of the anion. And vice versa. The number of the charge of the anion will cross over, drop down, and become the subscript for the cation. So in this case, we have Al2S3. Now that represents the proper ratio of cations to anions that allows it to be electroneutral. 2 positive 3s must equal and cancel out with 2 negative 2s. And therefore, you end up with that ratio. So let's take a look at another example. Let's say this time we have sodium chromate. All right. In this case, we have sodium. The symbol is Na. It's in column 1, so that's +1. Chromate, it ends in 8, so we look for it on the back of our periodic table, chromate, and we see that its formula is CrO4 -2. So we have CrO4 -2. It's a polyatomic anion. But again, we cross, drop, and reduce. The 1 crosses down to there, the 2 crosses down to there. So we end up with Na2, CrO4 1. And since you only have one of the polyatomic anion, there are no parentheses, and the formula is simply that. Let's take a look at another one. Let's say we have lead 4 oxide. Now lead, the formula for that, or the symbol for that, is Pb. When there is a Roman numeral, that tells you the charge of that cation. So since it's a 4, that means it's a +4 charge. Oxide, again, ends in "ide", so we look for the element that starts with ox, and of course that's oxygen. Symbol is O. It's in column 16, so it's a -2 charge. When we cross and drop, we end up at first with Pb2O4. But remember, it's cross, drop, and reduce. So that means that we have to go this 2:4 ratio. If you can reduce it, you must reduce it. A 2:4 ratio can be reduced down to a 1:2. So the correct formula is 1 lead for every 2 oxygens. So PbO2 is the correct formula for lead 4 oxide. And finally, let's try one more. Let's go with ammonium and phosphate. Now, ammonium is a special case. There's no element called ammonium. And I told you that you need to just memorize the fact that ammonium is a positive polyatomic cation, and its formula is NH4. And its charge is +1. Phosphate has, again, it ends in 8, so I look for it on the back of the periodic table. It's right here. It's PO4 and has a -3 charge. So we have PO4, -3. Now in this case, when we cross and drop, the 1, even though you don't write it, there's a 1 there, crosses over, drops down there, and the 3 crosses over and drops down there. Now the formula is NH4, but we need to indicate that there are 3 of the ammonias. And the way you indicate that you have more than one of a polyatomic ion is that you put the whole thing in parentheses with the subscript on the outside. So that 3 dropped down and went there. And then since we only have 1 of the PO4, we simply write PO4, and there's only 1, so there's no parentheses necessary. So the formula for ammonium phosphate is NH4 3 PO4. I wish you the best of luck. Thank you very much.